Hey everyone, Praveen this side. I hope you guys are doing great. And if you're not, keep hustling because one day you will definitely reach the heights of greatness. So today the problem title is smallest positive missing number, which is a medium level problem. So the problem description says you are given an integer array ARR. Your task is to find the smallest positive number missing from the array. That is, we have given an integer array. From that, we need to find the smallest positive number missing. The note point here is the positive number starts from 1. The array can have negative numbers too. Since it is an integer array, we can have negative numbers too, right? From that, we need to find the positive number which starts from 1. Simple. So the problem description is very clear. Now let's see the examples. So in the example 1, the array is 2 minus 3, 4, 4, 1, 7. And the smallest number is 3. The explanation says smallest positive missing number is 3 because we have 1, we have 2 and directly we have 4. We don't have 3 here. So the positive missing number is 3. And similarly, for example 2, the array is 5, 3, 2, 5, 1. And the smallest positive missing number here is 4 because we have 1, we have 2, we have 3 and directly we have 4. So 4 is missing, right? So we return 4. And in example 3, the array is minus 8, 0, minus 1, minus 4, minus 3. So the smallest positive missing number here is 1 because after 0, we have all negative numbers. So 1 is the smallest positive missing number. Now all the examples are clear, right? So let's take example 1 as reference and try to find few observations from it. Now we need to find the smallest positive missing number, right? So the first observation that I've observed is that for any array of given size n, what can be the minimum and maximum positive numbers? The minimum number will be 1 because it's already given in the question. What can be the maximum positive number? Suppose we have array 1, 2, 3, 4, 5. Okay. From this array, what is the smallest positive missing number? We have all the elements present, right? So what can be the smallest positive number? 6. And what is 6? 6 is n plus 1th number, where n is the size of the array. Agree with me? So the maximum positive missing number will be n plus 1. So whatever number we find will be within this range. Okay. Now with this observation, let's cross check this array. So we'll start with number 1. We'll check whether 1 is present. Yes, 1 is present. So we'll go to the next positive number, which is 2. And we'll check whether 2 is present in this array. Yes, 2 is present. So we'll go to number 3. Now we'll check whether 3 is present in this array. We don't have it here, nor here, nor here. So 3 is the smallest positive missing number from this array, right? So this is my first observation, that the number lies between the range 1 to n plus 1. Okay. And what is the second observation? The second observation is based on the first observation. Whichever number doesn't follow this rule will be discarded. That is, 3 will be discarded, 7 will be discarded because they don't have anything to contribute for finding our smallest positive missing number. Okay. So the second point is discard numbers that doesn't satisfy the above condition. Okay. Now keeping these two observations in mind, we can simply solve our problem, right? Now we need to iterate to the array and find the numbers which satisfy this condition. So the numbers are 2, 1 and 4, right? So I'll write it down, 1, 2 and 4. Now after separating the numbers, we need to find the gap where our missing number could be. So we'll start with 1 and check whether 1 is present in this. Yes. So we'll go with 2. Now check whether 2 is present in this. Yes. So we'll go with 3 and check whether 3 is present in this. No. So 3 is not present in this. So the result is 3. That we already know. But the thing is, we need to start from 1 and keep on incrementing till n plus 1 and check in this. So where can we store these numbers so that we can effectively retrieve it? One thing that comes in my mind is using HashSet. Right. Because with HashSet, we can easily retrieve whether the element is present or not in the set with constant time. Right. We can also store these elements in array also. But the disadvantage is to check this number, we need to iterate in the array. That takes the time complexity of O of n. Else the other approach is we can take this in array and sort it, and after sorting we can check whether the common difference between two elements is 1 or not. If the common difference is not 1, so whatever the number is missing, that will be the missing number, right? But that takes the time complexity of O of n log n, right? So the efficient approach that I found is HashSet. Although it takes the space complexity of O of n, but the execution will also be done in O of n. Okay. So this is the code in C++, although the logic remains same. So the function name is missing number and we have array as parameter. So firstly, I have taken unordered set. In C++, we take hash set as unordered set. Okay. After that, we are iterating in array and getting each number. This is the for of loop that we use in C++ to directly get the number. Instead of doing array of I, it directly gives the number. Okay. After that, I'm checking. If the number is greater than 0, to avoid the negative numbers, I'm inserting those numbers in the set. Okay. And after we are done with the loop, I've initialized number to find with 1 because 1 is the minimum number that we can find, right? And here I'm running a while loop till I find the number to find inside the set. I'm incrementing it and there will be a condition where the number to find will not be present in the set. We check whether the number is present or not in the set using this method. There are other approaches too. There are other methods too, but I find this very easy. So till that number is present in the set, we are keep on incrementing it, right? And there will be a condition when the number will not be present in the set, so this condition becomes false. So after this condition becomes false, it breaks out of the loop and whatever number to find is updated will simply return it. Okay, so this was the easy code. Now what will be the time complexity for this approach? Here we are running a for loop and here we are running a while loop. But we are also checking whether that element is present or not in the set. But as I said, retrieving any element from the set will take the time complexity of O of 1. So this loop will be O of n. So O of n plus this O of n will be approx O of n. Okay. And what will be the space complexity for this approach? Since we have used a hash set, so the space complexity also becomes O of n. Simple. So this was the code which was purely based on observations, right? So this was the brute force approach that we observed. But if we observe more, we can eradicate this space complexity. So let's see the optimized approach for this. Now, before moving to optimized approach, a quick observation from this number range is that our number range lies within 1 to n plus 1, right? So, is there any chance that this number lies in this array? Yes, right, because at 0th index we can find 1, at index 1 we can find 2, at index 2 we can find 3, so on. If and only if these numbers are present in the array. Are you getting what I'm trying to say? Like the optimal position for this 1 is not here, it should be here, right? The optimal position for 2 is not here, it should be here, right? And the optimal position of 3 is here, but we don't have 3 in this array. But if we had 3 in this array, the optimal position would have been here. So with this observation, what can we do? We can try to bring all the numbers within the range to their appropriate positions, right? And whichever position the number is not present, we can simply return the index plus 1 number, right? Because if we see the mapping, at 0th index we have 1, at 1 index we have 2. So if we don't have any number at ith index, so I plus 1 will be the number, right? This is the observation. So let's try to solve it. So we'll start with index 0. So for that, to check at ith index, we have ith element plus 1 or not. This will act as one index and an element inside that index will act as another index. I know it's overwhelming. What did I just say? You didn't understand. Let's dry run it once. Okay. This is not the intuitive approach. It is more like pattern based approach that if you had did this problem twice or twice before entering this problem, then only you can apply the logic. So we'll start with index 0. At index 0, the element is 2, right? So we'll check. At ith index, do we have I plus 1th element? No, right? So what we'll do? We'll take this as one index and the element inside the index as another index. But since this number is 1 base indexing, we'll do it minus 1 so that we can bring it to 0 base indexing. So if I note it down, at ith index will be 0, jth index will be whatever element we have, minus 1. And we are doing minus 1 because we are following 0 base indexing, right? Now, the element at ith index is 2 and at jth index where j is 2 minus 1 which is 1. The element is minus 3, right? So we'll swap the ith element index and the jth element index, hoping that the jth element brings us the array element which is I plus 1. because that's what we want, right? At ith index, we want I plus 1th element. So we'll hope at jth index, the element would be 1. Okay. So we'll swap. So the element now will become, this will be -3 and this will be 2. Right. Now we got -3 at 0th index. But as we see, -3 doesn't lie in this range, right? So we'll move our index to 1. Okay. Now let me clean this up. So we are at index number 1. At index number 1, the element is 2. So does it satisfy the condition? Yes, because at ith position, which is 1, we have I plus 1th element, which is 2. So we have 2 at its proper position, right? So we'll ignore this position and we'll move to index number 2. Now at index number 2, the element is 4. Now, is it satisfying the condition I plus 1? No, because the element is 4, but we want 3, right? So we'll take the index of it. So the one index is 2 that we written here, and the other index will be array of I minus 1 to convert it to 0 base indexing, right? So this, if we substitute here, we'll get 3, right? So we'll swap index number 2 element and index number 3 element. That is swapping this element and this element, right? So we'll swap it here by 1 and swap it here by 4. Okay. And again we'll check whether at ith index did we get I plus 1 element? No, right? And again, what will be the jth index? Here, array of I is now 1. So 1 minus 1 will be 0. So j will be 0, right? So we'll swap array of I and array of j. So we'll get here 1 and we'll get here -3. Okay. Now we'll check at ith index, are we getting I plus 1 element? First of all, it's violating this condition only. So we can't proceed further, right? Now if you check at 0th index, we got 1. At 1 index, we got 2. Okay. So whatever execution we were doing, with that, at least 1 and 2 came to its appropriate position, right? Now we'll move to index number 3. At index number 3, the element is 4. So is it satisfying I plus 1? Yes, because for 3, I plus 1 is 4. So this condition is satisfied. Now at index number 4, the element is 1. So the I is 4 and j is array of I minus 1, which is 0. Okay. Now we'll check whether these two elements are equal. Yes, these two elements are equal. So is there any need of swapping? No, right? So with this, one more observation is that whatever element we have at the ith index, if we have the same element at the jth index too, then there is no need of swapping. We can directly execute. So the three conditions that we observed till now is I should be greater than equals to 0 and I should be less than n. And the second condition is if we have same element at array of I and array of j, no need to swap, right? Because here at index number 4 and index number 0, we had same element, so we didn't swap, right? Now finally, at index number 5, the element is 7. Now we'll check whether this element is falling within this range. No, right? So here n plus 1 is exclusive and 1 is inclusive. Okay, that is the main point. Now after executing the whole array, we'll check whether at ith index do we have I plus 1th element. If this element is not present, then that will be the smallest positive missing number. Okay. So we'll start with index 0. At index 0, we have 1. So this is satisfied. At index 1, we have 2. So this is satisfied. But at index 2, we have -3, right? Which is not satisfied. So what will be the element? Whatever index we have, if we do +1 to that, then that will be the last element. So whatever index we are at, if we do +1 to it, so whatever number is generated, that will be the positive missing number. Okay, so at index 2, if we do +1, so whatever this number resembles, that will be the smallest positive missing number. Okay, again I'm saying that it is very overwhelming to understand what I have just explained. So better try yourself taking multiple examples, because if you try and write, you will get more clarity on that. So let's move to code now. So this is the code in C++, although the logic remains same. Again, we have the function missing number and array passed as parameter. I have taken the array size. From here, the actual logic starts. So firstly, in the for loop, I'm iterating from 0 to n. And here, I'm running a loop till array of I is greater than 0 or array of I is less than n. This was our first condition, right? If these two conditions satisfies, and when array of I is not equals to array of I minus 1, this was the j index that we are talking about. If this condition doesn't satisfy, then only we swap, right? Then only we swap array of I with array of I minus 1. Because whenever this gets equal, do we need to perform swap operation? We perform swap operation only when this condition dissatisfies. So that's why we are running a while loop. And after we execute this loop, and here we are doing our second step, that is, if at array of I we don't have I plus 1th element, then we are returning that element. But within this loop, if that element didn't get returned, so what could be the potential number? It will be n plus 1. The same example that we took in the starting, like if you have 1, 2, 3, 4, 5, all elements, so what could be the next smallest number? It will be 6, right? So that's why whatever n plus 1 element is there, we are returning it. So this was the easy code, right? Now what is the time complexity for this approach? Here, while watching the two loops, we might say that the time complexity will be O of n square, right? But that is not the case. Because when you die run, you will find an observation that each element will be swapped only once, right? It will never visit any element twice. So for this loop, the time complexity is O of n, right? And for this, the time complexity of O of n. So the overall time complexity will be O of n. What will be the space complexity for this approach? Since we didn't take any extra data structure like we did in our brute force approach, the space complexity will be O of 1. So with this, we have optimized our space from O of n to O of 1, right? So I hope you guys like this video. If you guys really did, then please like, share and subscribe to my channel. If you have any queries in any explanation, please comment it down. I'll respond it as quickly as possible. And if you have any concerns, and if you have any feedback for my teaching, please comment it down too so that I can improve on that. So see you guys tomorrow solving any other code problem. Till then, stay safe, stay happy, and peace.